Our goal here is to be able to calculate the directional derivative. We will reserve the second component of this lecture to focus on the gradient and how the gradient connects with the directional derivative and other applications. If you look at this diagram, and if you are somewhere on this mountain, and if you point yourself in whatever direction, it is possible to calculate the so-called tangent of the slope, which would change at various directions on this this incline. So we say that when you shift around and you focus in one direction versus a different direction, then you can control the so-called derivative based on the direction that you're facing. So our goal here will be able to calculate the directional derivative. Let's say, for example, at a point P here in the direction of Q. So we're going to point our arrow in the direction of Q from a fixed point P. And as Q changes, if you change your direction, then obviously the so-called derivative will change as well. We will say that this change from in Q, that is our terminal vector, is controlled by this angle theta. So as theta is changing, we calculate so-called different derivatives in the direction of theta, where theta will be governed by a unit vector that we will call u. So to be able here, our objective to calculate the derivative of a function f in the direction of a unit vector u. The direction is controlled by, the derivative, is controlled by the direction of u. The operator, that is u, would control the angle that u is determined by. So in other words, u control u. Well, I reckon that's enough philosophy for the moment. We do continue with philosophical notions of mathematics. Let u equal here a unit vector, cosine theta I plus sine theta j. For the two-dimensional space, we can raise that to the third dimension in terms of looking at I, j, and k, where x and y are defined here based on this diagram, and x and y relate with respect to p and q. The distance between p and q is said to be this number or scalar that we call t. And so x and y relate to q, and this x naught and y naught relate to p. So it is possible there to look at the distance between p and q in the xy plane, and to do that we have just the distance formula, and that gives us t, and that's what we're trying to calculate here and express between the difference between p and q. So if you look at the secant line, the slope of that with respect to f of xy and f of x naught comma y naught, that gives you this ratio. By letting t go to 0, we calculate not the slope of the secant line, but the slope of the tangent, and that gives us the directional derivative of f in the direction of u at the point x comma y. So we can calculate that by using the theorem that the directional derivative, if u is differentiable function, that is, of x and y. Here, the differentiability of f is said to be in terms of its partial derivatives, the partial of f with respect to x and the partial of ff with respect to y. So then the directional derivative of f in the direction of the unit vector u, given as cosine theta I plus sine theta j, is given by this formula. So the steps would be to solve for the directional derivative, determine the unit vector u. Sometimes it's given. If it's given, that's easy. If not, if an angle or a u is not given, then let v equal to the line segment PQ. That is, you take the terminal vector q minus the initial vector p to find the line segment, And then from there we can calculate a unit vector based on PQ as being V divided by its norm. Any unit vector has to have measure or magnitude equal to 1. From there, calculate the partial derivatives with respect to x and y, and if it's in the third space with respect to x, y, and z, and then use the formula to calculate the so-called directional derivative. Let's look at a few problems here. So what we want to do is to determine the unit vector. So u is cosine theta I plus sine theta j. Theta is given to be pi over 4. So here we have cosine pi over 4 I plus sine of pi over 4 j. So u comes out to be the square root of 2 over 2 I plus the square root of 2 over 2 j. Secondly, we find the partial derivatives, and that gives us the partial derivative of f with respect to x is 2x, and the partial derivative of f with respect to y is 2y. Now we are able to calculate the directional derivative of f in the direction of u here first at x comma y. So based on the formula, it's set to be the partial of f with respect to x times the cosine theta plus the partial of f with respect to y times the sine theta. So this gives us 2x times the square root of 2 over 2 plus 2y times the square root of 2 over 2. Now you can simplify that, and that looks like it's x times the square root of 2 plus y times the square root of 2. Now here we find the directional derivative of u of the function in the direction of u of the function f at the point x comma y. Well, it's at the point, and particularly at the point P, right? So at P. So the point P is given. X is 1, y is negative 2. So this is the directional derivative of f in the direction of u at the point 1 comma negative 2. So this gives us the square root of 2 plus this negative 2 hold your tongue. Okay. Negative 2 times square root of 2, and that gives us negative square root of 2. So the derivative here, you're looking at the derivative, but it's with respect to a direction. So this derivative is decreasing. Let's move on further. Let's do the same thing. You want to pay close attention to V. So V here is 3 over 5I plus 4 over 5J. Is V a unit vector? If not, we have to find U, calculate U to be the V divided by the norm of V. Well, let's investigate and look at the norm of V. So this is the square root of 3 over 5 to be squared plus 4 over 5 to be squared. So this is the square root of 9 plus 16 over 25. That gives us 1. So what this implies is that the unit vector is the vector V. So what you glean from that is cosine theta is the 3/5, and the sine theta is the 4/5. Now the partial derivative of f with respect to x is 3 minus 4y, and the partial derivative of f with respect to y is negative 4x plus 9. And so the directional derivative of f in the direction of u at here first x comma y is equal to, yes, 3/5, that's the cosine theta, times the partial of f with respect to x, 3 minus 4y, plus 4/5 sine theta times the partial of f with respect to y, negative 4x plus 9. Now we can evaluate this at the point 1, 2. It says at p. So we let x equal to 1, y is equal to 2. So we get 3/5 times 3 minus, here y is 2, so this is minus 8, plus 4/5. X is 1, so this is negative 4 plus 9. So we get negative 5 times 3/5. And then this is plus 5 times 4/5. So we get negative 3 plus 4. It just gives us 1. Move down to this problem. Let's check v. Make sure it's a unit vector. Well, the norm of v is equal to the square root of the square root of 2/2 to be squared. Hope you notice my tie. It has E equals to mc squared and plus some other mathematical jargon. And we're in college today. Okay. So the norm of v is equal to the square root of the square root of 2/2 to be squared plus the square root of 2/2 to be squared. That gives us 2/4 plus 2/4. That's 1. So v is the unit vector. Right? So cosine theta is the term times I, which is the square root of 2/2, and the term times the j, the coefficient, is the square root of 2/2 again. So the angle is pi over 4. Which you would have thought that it just could have told us that, and we could have just went on to that. But anyway, so we find the partial derivative of f with respect to x, 3x squared and the partial of f with respect to y is negative 3y squared. Okay. And so the directional derivative of the function f in the direction of u at x comma y is the square root of 2/2 times 3x squared plus the square root of 2/2, that's the sine theta, times this negative 3y squared. Now we calculate this directional derivative at the point P, 4, 3. So we have 4 squared, right? So that's the 16 times the 3. So this is 16 times 3 times the square root of 2 all over 2. Minus, we plug in y to equal to 3. So that gives us 9 times the 3 is negative 27 all over 2 times the square root of 2. So we get 8 times 3 is 24 times the square root of 2 minus 27 over 2 times the square root of 2. So we get 48 minus 27 over 2 times the square root of 2. So the directional derivative, and that gives us, let's see here, 10, 18, 21 over 2 times the square root of 2. Move on further. We examine this. Now, v, if you take its norm, we get the square root of 3 squared plus negative 4 squared, which gives us the square root of 9 plus 16. It gives us 5, the square root of 25. So indeed, v is not, it's not a unit vector. So we let u equal to v divided by the norm of v. And so this is 3 over 5i minus 4 over 5j. So that cosine theta is the 3 over 5, and the sine theta is the negative 4 over 5. Now the partial derivatives of g with respect to x. It's a nasty net. Whew, that's not good. So this is 1/2 times x squared plus y squared to the negative 1/2 times the derivative with respect to x, which is 2x. So that just gives us x over the square root of x squared plus y squared. And obviously the partial of g with respect to y, we have symmetry with x and y is the same, just replace the x with y. So it's y over the square root of x squared plus y squared. So we have the directional derivative of g in the direction of u at the point x comma y. So we have the 3/5 times x over the square root of x squared plus y squared minus 4 over 5 times y all over the square root of x squared plus y squared. So we look at this directional derivative of g at the point 3 comma 4 in the direction of u. So x is 3, y is 4. So we have 3 times 3 all over 5 times, this is the square root of 3 squared plus 4 squared, which is the square root of 25. So we get 5 minus 4 over 5 times y is 4 over the square root of 25. And that's 5. So this gives us 9 minus 16 over 25. So we get negative 7 over 25. So one more here and then we'll take a break. Use the theorem to find the directional derivative of the function at p in the direction of q. Well, we're not given a unit vector and we're not even given v, so we have to let here v equal to pq. So let v equal the line segment pq, which is 4 minus 1, 3, comma 5 minus 1, 4. And the norm of v is the square root, looks like a previous problem. 3 squared, which is 9, plus 4 squared, 16. So we get the square root of 25, that gives us 5. So u is equal to v divided by the norm of v. So this is v is here. This is 3 over 5 I plus 4 over 5 j. So we use those values for our unit vector. Now the partial of f with respect to x is 2x, and the partial of f with respect to y is 6y. Now you can find the partial of f with respect to x at the point 1, 1 at the point P. So this is 2, and then the partial of f with respect to y at the point 1, 1 is 6 times 1. We get 6. So our partial derivative of f in the direction of u at the point 1, 1 is, again, look, the partial of f with respect to x, at the point, right? 1, 1 times that cosine theta plus the partial of f with respect to y at the point 1, 1 times the sine theta So this gives us the 2, which is the partial of f with respect to x, times the cosine, which is 3 over 5, plus the partial of f with respect to y, 6, times the sine theta, which is 4 over 5. So that gives us, yes, 6 over 5 plus 24 over 5. So you get 30 over 5, and that just gives us 6. Thank you.